Uh, oh dear, oh dear, oh dear, oh dear. This is not good. This hopefully should be better. So yeah, hello. Hopefully you are able to see and hear me even on the full screen. Wait, why is it cropped? Never mind. Yeah, so as usual, the time is now. It's 5 p.m. UTC on Thursday, and that means Iron Middle, a show where we try to describe how this awesome Capital database works inside. How you could implement database which doesn't allocate memory at runtime, which is fully deterministic, which is awesome in each and every way. And yes, I'm traveling, so today's episode is going to be is going to have a larger share of technical issues, but like traveling is not an excuse for not doing an error middle. So, okay, what are we going to do today? Well, as usual, Brian, uh, we are going to talk about compaction. So, as a reminder, the last two episodes, we did a ground recap where we understood how all the bits and pieces of Dagobah fit together, and today, and well, starting from this episode, we are actually going to send off various features of Capital which we haven't fully covered yet. Before our recap, we've spent like 6, maybe 7 episodes working through compaction, and I was like complaining that hey, this is code is like hard to understand, and maybe it could be written in a slightly more straightforward way. And I actually went and did that, and I have a compaction refactor, which is what we are going to discuss today. So now let me try to share my screen. Okay, and let's dive in. Yeah, more compaction. More compaction is always good. Uh, Okay, and by the way, the pull request is still in review, so if Federica is watching that, then that's great. Otherwise, if someone from Targetable is watching this, then please ping Fed to join this, because yeah, this might expedite the review. Okay, so um, compaction, and before we start reviewing, let me actually show you one editor trick. So yeah, essentially, we want to look at the diff, which is was applied by a single pull request, and that pull request has, like, as usual, a couple of commits. So there's like the main commit, and then because GitHub pull review is not good and doesn't allow inter-diff reviews, there is like three commits which correct various code review issues. And like kind of like, in the editor, you want to review the whole thing about, like, you could kind of like click on an individual commit and that like shows you a diff, but that's like, not really super convenient. You kind of like want to see this in the code. And what I usually do in this case is that I go and copy the commit hash, and then I open my terminal and I say git reset. What I say? I think I say just git reset this commit, and then I get this. Well, I get the stage. Then I also unstage everything, and then whatever changes I have, I can actually see them in my editor, and I can navigate through them using like next change, previous change shortcuts. Okay, so that's what we're going to look at today. Okay, so what was the big deal with compaction? The big deal with compaction was pipelining. That okay, I think I might be. Well, I'm not too small. The big deal with compaction was pipelining. Compaction needs to do a lot of concurrent work, and our plan was to kind of like enable to like do this concurrent work actually concurrently instead of sequentially. So for example, we would really love to pipeline reading, merging, and writing. So compaction needs to read blocks from both input tables, merge them, and write outputs. And as soon as you have written one block from one level and one block from another level, you could actually go and start merging those blocks, while at the same time you are reading the next blocks from both levels. So that is the kind of concurrency we want to enable. Okay, so the kind of like high-level change is the change for the interface of compaction. So we renamed compaction pipeline to compaction schedule because now it actually doesn't do any pipelining in and of itself, and instead of compaction schedule is responsible only for scheduling different compactions relative to each other. Okay, I think my microphone might be too close to my face for my comfort. Okay, so what do we do this? With this compaction schedule, it's I think should be relatively straightforward. Yeah, basically we say compaction schedule, please start the work you need to do for this bit, and when you're done, call this callback. Then in this bit start, what we are going to do is that we are going for every compaction, just go and call. It's not true that for every compaction. Okay, so kind of like we want to go and call bar commands for every compaction we have, and then we want to call bit commands, and then we want to actually step through the work each compaction needs to do in this bit. So the thing here is that compaction schedule no longer tries to track the set of active compactions. Instead of we call bar commands and bit commands for just every compaction there is, and it's up to an individual compaction to not do the work if it's not needed. So if we see, for example, bit commands, well, not bit complete, bit comments. Okay, yeah, so you see, each compaction individually could say, hey, actually, I have already done my share of work for this bit, so I'm just going to return immediately. Okay, so now, what work are we actually doing? As a reminder, our compaction is deterministic and perfectly paced. That means that we have 32 bits, which is allocated for one round of compactions. We run half of the compactions in the first half of this 32-bit bar, and we run the other half of compactions in the second in the second half of this 32-bit bar. That is what level active function is doing here. So we just say, hey, given this level and this op, should we be running compactions on this level, which is that for the first half we run odd compactions, and for the second half we run even compactions. Okay, then let's see what we do. Well, first, bar comments. Here we schedule the work that compaction needs to do for the entire bar, which mostly means just selecting the tables we need to compact. So if we are compacting into level 0, that means that we are compacting from immutable table. And that's why we say we set the table info A to be just a slice of values. So this immutable thing is just raw slice of values. And then for our range B, we ask our manifest to find out all the tables which intersect, which could intersect our immutable table, which we figure out by giving k-min and k-max of our immutable table. So that's it. For every other level, both table A and table, both levels are going to consist of tables on disk. So that's what we actually do. We go to the manifest and say, hey, manifest, please figure out which table you want to compact if needed. Again, here, it actually might be the case that our level A is not full, that there is just a space for one extra table, in which case we just say, hey, there's nothing to, well, there's bar commands, nothing to compact. Okay, perfect. The second thing we do after we determined the set of tables we need to compact for this compaction is to figure out our quota. So quota is a new construct, and quotas determine pacing. Here for the bar, we are going to determine the bar quota, which is to say just the total amount of values in all of the input tables. So we just sum up all the values in table A and table B. We don't have the tables themselves. Of course, the tables are on disk, but we do have meta information about the tables. We store the size of the tables in the manifest log, so we could actually go and look this up. So yeah, let's start with level A. Okay, if this is immutable, then just the number of values in that slice is our starting quota for level A. If this is disk table, well, there is value count for this on disk table. And then for range B, we just iterate over every table and append this quota. So, okay. Now we know which tables, which table from level A we need to move to level B. We know which tables on level B intersect with this table from level A, and we know the total amount of values which we need to move. The total amount of values would be useful to slice our large amount of work into more manageable pieces. Now, as a special case, we might be in a move table situation. Specifically, we are in a move table situation if we are merging a table which is on disk into a level, and that level doesn't actually have any tables which intersect with the current table. In this case, we could avoid doing any disk I/O and just directly change the metadata. Say that, okay, this table was like on level 6, now it is on level 7, or something like that. So if this is a move table, then we just go and immediately apply. Well, we are not immediately apply because indeed we'll actually apply changes to the manifest at the very end of compaction, but we just record that, okay, we want to just move this table from one level to another, and that means that we actually went and fulfilled our quota for the bar and for the bit. Now, okay, what is quota for the bar for the bit? And this is what we are going to do in bit command. So let's go back our let's go back to our forest. So okay, we have these bar commands which we called for first bit or half bit, so when we are starting individual compaction. And then for every compaction which is active, we go and call bit commands. So the main thing that bit commands is doing, well, actually, I think it's like more or less the only thing that it is doing, is computing the quota for the current bit. So, okay, let's see how it is done. We have our total quota for the bar, and we have the number of values which we have finished with in the previous bits. So quotas bar minus quotas done is the work that is remained in this compaction. Now, we have certain amount of bits remaining to do our compaction work. So let's check how this is set. Bits remaining is basically the bits remaining in the half bar. So, okay, as an example, our op is 17. Our op is 17 means that we are the second bit of the first half bar. So bar is 32, half bar is 16. So bits total is 16. Now compaction bit is 17, half bar is 16. So compaction bit modulus half bar is 17 modulus 16. It is 1. So bits remaining is bits total minus 1. It is 15 bits. Okay, so we have this amount of this bits left. We have this amount of values left. So we divide with ceiling one by the other, and that is our quota for the bit. So in the current bit, we should go and fulfill this amount of values. Okay, now what does it mean to fulfill a bit quota, and what is? Okay, let me try this. What does it mean to fulfill bits quota, and what does it even like quota means? Well, we count our input values, but we need to remember that whenever we merge input values, they actually might get annihilated with each other if there are tombstones. So it is not true that, like, if we have like 5 values on the input, we'll have 5 values on the output. We actually could have less than 5 values. And our quotas count input values. But It is also desirable that when we are merging things and producing output, that we don't end in a middle of a value block. So remember, the structure of our table is that there is index block, and then there is like a bunch of values blocks. And like if our quota in terms of like input values is like 100, and we process like 100 values, it might be the case that our currently the table which we are writing to disk, it might be in a position where the output value block is only half full, and that is not good. That is not good because then we'll have to carry over this half block for this compaction over to the next bit. We need to keep these values in memory, and we would like to avoid this. So we actually want to say this. We want to say that the bit work is done once we fulfilled our bit quota and once we have outputted a full value block of output. So in a sense, value quota measures the output value blocks, and each output value block weighs exactly as the number of values that contributed to creation of this value block. So we want to finish our compaction for a bit when we have outputted a full number of value blocks, which contain at least our quota of input values. Okay, so let's get back to our code. That means that given our quotas for a bit, we could actually estimate the number of blocks we could create. Kind of like, roughly, this is number of values we have to process in a bit divided by the maximum number of values we could feed in a single data block, plus 1, exactly for a case where when we finish our values quota, we have a block half full, so we need to, like, we need to fill one more block. And then, those output blocks are going to be filling tables, so we might need some amount of index blocks. And that we also can compute. So in the end, from this quota, which is formulated in terms of values, of input values, we could get the estimate of the upper bound for the number of output blocks we produce. And that allows us to reserve certain amount of grid blocks for allocation. And it is important to see that this bit commence function is actually synchronous. There is no callback. So, we are going to run it for all the compactions at the same time. As a result, our actual allocations of grid blocks are deterministic. Well, our reservations are deterministic, but because each compaction is going to allocate only from its own reservation, then even if we run compactions concurrently, their allocations are going to be deterministic. And as a spoiler, we aren't actually going to run compactions concurrently just yet, but the code is fully prepared for that. Okay, so after we have our bar commands and bit commands, each compaction knows which table it must move from level A to level B. It knows which tables on level B are intersected, so which tables it should read and merge with level A. And it knows its quota for a particular bit. The actual work happens in this bit resume function, which is like now it is like super simple. Like before it was like this like horrible pipeline thingy. Now it fits in one function. Like fear not, there's going to be a horribly complicated function which we'll look at in just a moment. But first, let's see how bit resume works. And it's like super simple. For every compaction, it asks this compaction to do a work for a bit, which is asynchronous, so we pass in callback. And compaction might say, hey, actually, I've already done the work for the bit, in which case we'll just return, we'll just continue with this for loop for the next compaction. Or the compaction could say, hey, actually, yes, I do have the work to do. So I will call you back later using this callback when I'm done. And in this case, we go and actually return from this function. And then when this callback is called, we enter back into our resume function and continue to return compaction. The compaction which previously caused us to like do this time is going to return bit finished. So we go and we'll proceed to the next compaction. So this is kind of like, essentially it is a for loop over all compactions, but it is implemented like super inefficiently because we don't actually remember the index from which we should start. For simplicity, again, it's going to be trivial to do. But that means we understand this compaction dispatch enters contract. The job of compaction dispatch enter is to do a work for a single bit of compaction. And now we go to the mid of compaction. We go to the lovely compaction dispatch function. Compaction dispatch. So here it is. And it has some comment, and then it goes and goes and goes and goes and goes and goes and like adds like, I don't know, 200 lines later. So this is a mid function, and this function does the actual loop of compaction. So this is kind of like the scary stuff. Okay, so why is this complicated? So remember that we want to pace our compaction work over several bits. So for like a single bit, we actually don't do like, the whole compaction thing. We only do the work allocated for this bit. And then we kind of like resume this work for the next bit. So the way this function is written is that compaction dispatch is essentially like, that whole loop which runs through the entire bar of work for compaction, but internally it will kind of like just pause at the bit boundaries. So essentially, like, this compaction dispatch is going to be called again and again and again. So like, when we call compaction dispatch enter, we call compaction dispatch. Compaction dispatch will end up calling various functions, which will have various callbacks, which will let me check some example. Which will like essentially like tail call compaction dispatch back. So this is essentially in a big while not done loop. Okay. Now the job of compaction dispatch is to schedule all the compaction work as concurrently as possible. And the idea here is that we want to have this like pipeline structure at runtime, where like while we are merging values from the beginning of our levels, like we are going to read the following values, and like once we finished merging, then we start writing values to disk while we continue merging and continue reading, etc., etc., etc. So originally we kind of like explicitly encoded this structure in the code. In this approach, there is like no explicit encoding in the pipeline. Rather, pipeline arises naturally from the structure of the code. And what is the structure of the code? So the idea is this. It's kind of explained in the comment. We think of compaction as a bunch of work items. So like, read index block from level A, then read first values block from level A, then read second blocks from value A, then read index block from value B, then read index block from value B, then value block, then merge value blocks, then like right. Basically like a lot of like individual things we need to do. And there are dependencies between things. Like obviously, like you cannot start reading the value block until you have read the index block, and you cannot start merging stuff until you have two value blocks. So the idea here is that we'll kind of like just we'll try and start every job we could, as long as we have the necessary prerequisites. So like you don't start reading the value block until you have index block, but if you have index block, like you just go and start. Now, how we track these dependencies? We track them in the compaction. Okay, this is really horrible, and at some point we should probably try to compress this, but well, it is what it is right now. So we track them in the compaction, which is here, and in the so-called resource pool type. So let's start from the compaction bits. And let's go through level B, because level B is actually like more general. So for level B, we need to have index blocks. We need to read index block, and after reading the index block, we need to read value blocks. Well, actually, okay, let's start. Let's not start from the beginning. Let's not start from the end. It's like just boring. Let's start right from the middle. Okay, let's say that like we want to merge blocks. We want to take one block from level A, one block from level B, and we want to merge them. To set this up, we are going to have two queues, two ring buffers for level A blocks and level B blocks. And when we are going to read blocks, well, we are going to push them into those queues. And when we are going to start the merge, we will check that we have something in level A and something in level B. So if we see how merge is written, okay, this is going to be in the merge inputs. Okay, so you'll see kind of like in the merge, we'll for level A, we'll go into this level A value block queue and look at the head element. And for level B, we do the same. And the condition for like getting into this merge is that we actually have a block here. So like there is like level B ready means that we actually have an item in this level B value block queue, and the block in this queue is in read value block done state. Okay, so now we kind of like understand the like middle of things. Like we want to get two blocks in these two queues in the read value block done state. Then we can proceed merging. Let's go like backwards from there. So what is like read value block done? Well, it is a stage of a block, and before a block gets into read value block done state, it gets in read value block, and read value block means that like IO is in progress. And like now you kind of like see this like structure of this code. We are going to start reading a block from level A, which means that we'll push a block to the end of this queue in the read value block state. Once we've finished reading the block, which will happen later, we'll go and change the stage of this block from read value block to read value block. Done. And there might be like further blocks ahead of it in the queue, and those further blocks will be fetched by the merge queue. Okay, so this is all the queues we have. So kind of like we covered like level A and level B. Now for level B index blocks, like level B has many tables, so we actually could have like a queue of index tables we are going to read. But it is actually enough to have just a single table. I mean, like you could have like more tables to like enable more pipelining, but like usually you want to pipeline several blocks, not the entire table. So like we use just queue of length 1. And for level A, again, there we have one table in total. So actually here, like instead of a queue, we could have used just null pointer or something like that. But I decided to use a ring buffer as well, just for like uniformity. And then there is like the same thing for the output blocks. No, I don't need dictionary here. When we want to, when we start writing block to disk, we actually go and add it to the output blocks. And once it is done, we go and fetch it from the output blocks. So, okay, this is kind of like the structure of the dependencies between the jobs. We have a bunch of like ring buffers, a bunch of queues. We enqueue elements to the end of those queues. When we start IO operation, when we finish IO operation, we flip the stage to done. And when we want to use results, we look at the head of the queue. And if the block is in done stage, then we can go and pop it off the queue and use it for merge. Okay, perfect. Now, the second component, the resource pool. To do IO, we'll obviously need like memory to read blocks into, and we'll need read and write IOPS. We need read and write slots because again, everything is statically allocated, including the memory for all asynchronous operations. And here, this big idea of pipelining across compactions. While the current code in the forest, as you have seen, runs on a single compaction at a time, as the same as did the previous code. We do want to allow all compactions, well, not all compactions, but several compactions to run concurrently. And we want to share resources between compactions. We want to allocate, we don't want to allocate dedicated resources for each compaction, because that would mean that we'll have like too many memory wasted. We want to actually do some amount of manually managed dynamic allocations. We want to manually dynamically allocate resources between compactions, and this is what this resource pool type does. So resource pool lives at the forest level. So you see in the forest there is compaction schedule, just a single term in the forest, and in compaction schedule there is this pool. Are you here, pool? Yeah. In compaction schedule, this is this single pool. So, but this thing is shared across all compactions. And when compaction would need a read, a write, or a data block, it will try to fetch it from reads, writes, or blocks. So reads and writes are standard IOPS, which we have seen already. And blocks is kind of like manually implemented IOPS for unbounded number of blocks. So let's see, add block acquire. So we want to acquire a block, then we pop a block from this FIFO, assert that it is free, and return it. When a block we want to release block, similarly we assert that the stage is free, and then we push this on this FIFO. And when we allocate this resource pool, we pass in the number of blocks we want to allocate, we pass in the allocator, and then we will just go and allocate all the blocks, like super simple, super trivial. Okay, so now we can actually go and see our compaction dispatch loop. Okay, this is going to be slightly complicated. Let's ignore this for now, because this is the end of the loop. Then the first thing we do is that we'll take our pool and we allocate blocks for table builder. Table builder needs at least 2 blocks. It needs an index block and it needs a data block. And this is exactly what we do. We allocate block for index, allocate block for value blocks. It might fail. It might be the case that, hey, there isn't actually any blocks in the pool. But this could only be the case if some block is already used for compaction for some other purposes. In particular, if some other block is already is being outputted. So and this is kind of like deadlock prevention. We cannot deadlock waiting on output blocks, because if there isn't a free output block, then necessarily we are writing something out. So this means that there is an outstanding write to disk, and that write will finish at some point, at which point, well, we'll have our block back. Okay. Now, we need to read something from level A and something from level B. For level A, of course, we need to read something only if level A is actual table on disk rather than in-memory table. So we only do this for level B greater than 0. To read something from level A, we first need to read an index block and then read a value block. Okay, so when we can read an index block? Well, first of all, if our queue of index block is not full. So the second role these queues play is that they actually limit concurrency. They say that, okay, so you could read like LSM compaction queue read max divided by 2 level B value blocks, but you could not read more of them. So that's kind of like that's the limit of concurrency here. So okay, if we can read the block there, and if we haven't actually have read the index block yet, so this level index block next is, well, one complicated thing about compaction is that like level A is a special case, and you always want to start reading from level B, because level B is like, more simple, more general code. But like because A is before B in the alphabet, sadly the code is written with like level A first. I wonder if we should just rename A and B here. Well, anyway, what I was talking about, yeah. So we have this level A index block next. Well, I have like level B value blocks. Level B index block next. This means that, hey, the next index block we should read from level B is this one. So in compaction, we have range B, which is just a bounded array of tables. And this level B index block next is essentially an index in this thing. To keep the code similar, I actually use the same structure with level A index block next for level A, although I know that on level A there is just a single table. So anyway, yeah. So if we have space in our queue, and if we have yet to read the table, and if we have managed to acquire a block, then we acquire a read and this implementation. We actually statically size the reads such that reads are always available. So basically we set the number of reads equal to the total size of all the queues. In a future work, it is planned to actually relax this and to have something like if compaction pool reads acquire here and handle the else. But for now, for simplicity, we don't do this. Okay, so what we do? We flip our block stage to saying that we are going to read the index block. We enqueue this into this ring buffer, and then we start read index block operation. Well, let's see how read index block works. It should be relatively straightforward, or maybe not. Before we do that, let's see that for level B we do essentially the same, and it's literal copy paste. It infuriates me that this is like literal copy paste, but I haven't get to reducing this as well, because kind of level B and level A are the same, but level A also could be immutable. So you'll see here, like, a lot of code in compaction is like actually written 3 times. For level A immutable, for level A on disk, and for level B on disk. And that's like stupid, but well, it's still on to do to reduce this. But anyway, for level B index, we do the same thing, and then we call read index block with necessary level. Okay, so how do we read an index block? Well, we need the address and the checksum of the table. For level A, this is our table info A. For level B, it is our compaction range. Get the actual block we are reading. Okay. And then we go and kindly ask our grid to please go and read that block either from disk or from any other replica. And then we advance this level A index, level B index. So the next time we wrap over the compaction dispatch loop, we'll actually go and read the next table. Again, provided that we do have space in our queue, which we probably wouldn't because our queue is of length 1. But for value blocks, like you'll see, that's the same structure. Okay, so ask the grid to read the block. When we have read the block, we don't do nothing. We just say, okay, that like now the block stage is read index block done, and let's resume compaction dispatch. As a reminder, this block is now in level A or level B index block queue. Okay, so let's start to fold things we have already covered. Okay, then we are reading value blocks. Again, to read value blocks, we actually need to have an index block. Because if we don't have an index block, well, we cannot read a value block. So if we have an index block, and if we have free space in our level A value queue, then, and yeah, I'm kind of like trying to make it so you don't notice like some extra conditions I'm skipping over. I will get back to them. So yeah, if we have space in our value queue and we could acquire the block, then we go and we read the value block, which is like very straightforward. So we want to read the value block. We need to fetch the index block, and we know that this index block is the head of our queue. And actually here, we should, okay, this is missing an assertion. Index block done. Okay, this one is missing. Okay, and now we have this index block. Then we using the same value block next variable, figure out like which value block we should fetch from this index block. Then we get the address and the checksum of the corresponding value block, and kindly ask the grid to go and read the block. And then we again increment this counter which says which index block, which value block we should be reading next. But there is the case where actually what we've read is the last block. Well, let's see, level B, because again, level B is general case. It could be the case that the block we've read is the last block in the table. in which case we can actually now go and remove the index block from the index queue because, well, we've read all the value blocks there. That's what we do. We just release value block, and then we reset our index to 1. Okay, now let's try to explain the complicated stuff I've skipped over. Okay, first complicated stuff, level priority. Again, we have blocks on level A and we have blocks on level B. And we kind of want to read both of them. And again, remember that the total amount of resources is restricted. We don't have infinite amount of blocks of memory available. And that means that there could be a problem. There could be a problem if, for example, we start and we read level B and level B and level B, and we have read all the blocks from level B into our memory, and but we don't have, and we've run out of blocks, and we cannot read any more blocks from level A, and that would be really bad because that would mean that we've deadlocked. We've read all the blocks from level B. To kind of release those blocks, we actually need to do the merge, but to do the merge, we need at least one block from level A. So that's why in this queue there is also this rule that you could only read a block from level if the other level has fewer blocks. And this is what level A priority thing does. It basically checks that the number of blocks currently in queue for reading is less than in another level. Okay, that's the first complicated thing. The second complicated thing, this avoid overread at the end of the bit. So this is about this thing. We kind of have this extra requirement that we should stop when we produced a full table. But actually, we never know when we produce the new table because the values could be destroyed during tombstones. So once we fulfilled our quota and there is a little bit of extra space we need to still fill in our output table, we need to we need to at least read one more block. But actually it could be the case that every value in that block is going to be annihilated, so we'll go into read more blocks, etc, etc, etc. So that's why we kind of do this heuristic here, that when we are in a case where we fulfilled our quota and we've already have 2 value blocks read, then we actually shorten our read queue to just 2. So this level A value block is actually pretty sizable queue, so we could read. Actually, I don't know what is the size of this thing. It is 8. So we could read up to 4 value blocks at the same time. But when we are in this bit finishing state, we actually cut the size to 2. Okay, so I kind of hope to cover the entire new compaction in one sitting. This obviously didn't pan out. So I guess in a week at 5 p.m. UTC live on Twitch, we'll see continuation of this. But I think we've actually covered, well, at least, well, maybe this is because I've been hacking on this code for a couple of weeks and it's really fresh in my mind. But hopefully for some of you as well, it is relatively clear what we have done today and what is the role structure and how it's going to end. So we first of all, for each compaction, we decided on what tables we need to merge at all. So if the level is not full, then we kind of skip compaction work. If the level is full, then we need to select one table from level A and all the tables from level B that intersected. So it's kind of we plan the work for the bar. Now, after we have planned the work for the bar, we then actually go and count the number of values for level A and level B for this compaction to determine the quota of input values for the bar. Now, we start the bit work. And for the bit work, given that we already know the quota of values for the bar, and given that we know the quota of values which we have already processed, we can estimate like how many values are there left to be compacted, and we know how many bits are left. So that allows us to determine the quota for the current single bit. Given the quota for a single bit, we can estimate the total number of tables and blocks we are going to allocate, and we are going to make this grid reservation. So that is the setup, which happens sequentially. Now the concurrent part. Concurrently, we run this dispatch loop, which is set up in a way where we try to fire off a bit of compaction work every time we actually have resources and dependencies left, where resources are tracked in this resource pool and dependencies are tracked into this structure of queues, aka ring buffers. So again, for kind of like a level B, if we have space for reading the index block, then we read the index block. And then once we have read the index block, if we have read the index block, so if it is actually done, and we have space to read the value block, then we go and read the value block. So next time, I guess we'll start from this point on and look at this lovely, I don't know, like, you know, English name has like collective names for all the animals. Like there's like a pride of lions, a school of fish, a conspiracy of lemurs. I wonder what is a collective number, what is a collective noun for a bunch of variables. So anyway, I don't know, a throng of variables. We'll look at this thing next week. Thanks for joining, and sorry for less than kind of like, well, for slightly unusual audio and video and aspect ratio setup here. Goodbye and see you in a week. Okay, now I should suppose to do the